My name is Jackson. I'm from group 19, and from our preliminary lab, you can see this is the value obtained here, and we can conclude that the state diagram is we start from 000 to 010 to 101 to 100 to 110 to 001 and back to 000. From the circuit, we can see, okay, we'll start from 000, 010, 101, 100, 110, 001 and 000. That's all. Thank you. Hello, it's me again. I'm gonna continue explain from what we have missed in part 1, which is these questions. How can the state of F be forced to a particular value to allow the transient state to be turned? So our conclusion will be we connect the wire KA and KB to the switch. Okay, I'll show you here. Switch here. Use low to set A and B. Use high for usual operation. So if we press, let's say, okay, look at this now. It's changing between 011 to 011 and 111. Yeah, these two values. But when I press both of it, which is high, it will 00, 00, 101, 100, 110, 001, and back to 000. Okay. So if it's low, okay. So if I press this from 111, 000. 011, 100. Thank you. I see.
Hello, good morning. My name is Yasin, and this is for Lab 3, Part 2A. So Part 2A is about construct a reverse 8-bit light chaser. So this is the schematic that the logic that shows here. So we have a counter here, HC161, and a multiplexer, HC138. So how does a reverse 8-bit light chaser works is like when the HC161 as a counter are connected to a clock and a switch here. So it will like produce a count for, like for example 000, and then 000 will go to the multiplexer 000 and produce and light off one of the LED, like switch off the LED module, that is the first one. And then when it is also checking if the 000 and then to the NAND gate, which is HCT10, it will check to the pin 9 of HC161 is it 1 or 0. If it's still 1, for example 000, and will produce 1, it will still continue for 001, 010, 011, 100, 101, 110 until the moment is 111, where 111, when it's count 111, it will produce 0. 0 to the pin number 9, because 9 is active flow, it will reload to 00 again, where the LED will off, start from the first LED and continue off, and continue reload. And for example, we can see here, yeah, 00, see, it's true. And then reload again, boop, and this will continue on. So this here is a multiplexer which connected to the LED module, and the counter are connected to the clock and switch module. So switch module are used to count the 00, 001 stuff to reverse the 8-bit light chaser, and the clock module are used to speed up the frequency of the on and off of the light. So this is for answering the part 2A reverse 8-bit light chaser. Thank you. So as you can see here, the counter which are connected to the switch module, this here is to on and off the counting. For example, this state is on, so the counting is on here. So when I switch it off, so the counting are stopped. But when I turn it on, so you can see the count will start again from the off step. Here, the count will start here again. See, like that. Okay, that is 8-bit light chaser. Thank you. And also when it's like 111, right, it turn into 0, the AND gate, which is XCT10, will say like, hey bro, it's 0. So the active high of the counter SC161 will say reload, and then everything turn to 0, and then the counting start all over again. Counting start all over again from this part, this in a reverse way. You can see that D7, 6, 5, 4, 3, 2, 1. The speed 111, reload 00, 001, 0, 011, 01, and so on. 111, reload. Look.
Hi, it's Loh. I'm going to talk about D.E.D Lab 3 Part 2B, which is implement this function by using 8-to-1 multiplexer and a single gate. And the gate we use is a NOT gate actually. Yeah, it's a NOT gate. That we change our D into D0. But in fact there is no we don't have a NOT gate IC, that's why I'm using this logic, which is connect D and input 1, which is a VCC, and it goes through a NAND gate and then it will come out. The output is the same, it's just that I'm using a NAND gate for our NOT gates. And this is the table that I draw by using that function. And based on the output, I realized that there is 1, 2, 3, 4, 5, 6, 7, 8. There's 8 input. We need to have 8 inputs. So as you can see here, A is our S2, B is our S1, C is our S0, which later we will connect to our multiplexer. Actually, these 3 is the selection gates of our multiplexer, and only this will be our input. The D will be our input. So as you can see from this multiplexer, how the logic works, that these 3 will be our ABC. In this case, it's C, B, and A. So these 3 will select our which gates it will go. So based on the table here, so I come up with input 0, which is this gate. It's connect to 0, and input 1 connect to D, input 2 connect to 1, input 3 connect to D0. Yeah, this D0 is based on this NOT gate. I mean this gate actually we are using. The actual gate is this, but the logic gate is this. Yeah, the actual IC we use is this. I4 is D0 also. Input 5 is 1, input 6 is D, and input 7 is D0. So this is the whole input that we use, so that the real circuit is here. So as you can see from the table, from this table, when the selection gate is 0, 0, 0, 0, it doesn't matter if your D is 0 or 1. Let's show you. You see, if input is 1, the output is still 0. Doesn't light up. It doesn't matter. Yeah, it doesn't matter. So as you can see, the second one, these two, the output of the light, this thing, is based on our D. So when we select 0, 0, 1, if the D is 0, 0, 1, if the D is nothing, the output will be nothing. If it's 1, the output will light up. Yeah. And then for the third one is 0, 1, 0. It's based on, it doesn't matter because the output is 1. So 0, 1, 0, it doesn't matter what your D is, the output is still 1. And for 0, 0, 1, 1, the output is based on the inverse of our input. So that if I press 0, 1, 1, there's no D, D is 0, output is 1. If D is 1, output is 0. Yeah, it's the inverse of it. Yeah. And for 100, 100 also is the inverse of our input. See, 100, I don't press a D, output is 1. If I press a D, output is 0. So it's the inverse. It's the inverse. Yeah, wait. It's the inverse of it. So for 101, the output will become 1. It doesn't matter what your D is. See, if I press D, yeah, it doesn't change anything. It doesn't matter because it's 101. 101, you don't care about your input. So until 110, 110 follows the D input. So you say 110. If D is 0, output is 0. If D is 1, output is 1. Yeah, D 0, output 0. D 1, output 1. Yeah. And for the last one, 111, the output is based on the D input. So if wait, let me check if I can just light up all three and make them stay. And then I'll just press it. If it's 111, I didn't press my D yet, so the output is 1. Yeah, it's the inverse of my D, as shown here. Yeah, if it's 0, it's 1. If it's 1, it's 0. So if I press 1 as my input, the light will go off. Yeah, yeah. See, for light up, if this one goes off, this one will light up. Yeah, and that's it for the 8-to-1 multiplexer and 1 gate. Yeah. Hi, it's Jia Chiew here, and today I'm going to talk about the part 3 of D.E.D Lab 3. So for part 3, we are required to do this circuit, and this is the schematic of the circuit. So for this circuit, we draw a truth table here, which is here, and the K-map at here. So at K-map, we can know that there is static 1 hazard occur when 111 is changed to 101, and static hazard 0 hazard occurs when 000 is changed to 010. In this case, we only do static 1 hazard, which is 111 to 101. So for our inverter, this inverter, we don't have a real inverter for our IC. That's why we're using this logic. We use a 3 NOR gate to exaggerate the delay and the hazard effect. So as you can see the theory here, that when 111 is changed to 101, the static 1 hazard will occur here. So this is our real circuit. So you see, this is A, this is B. This is A, this is B, and this is C. Our AC is 11, which doesn't change, and our B is changed from 1 to 0 and 1 to 0. It's continuous. So you can see from this oscilloscope that static 1 hazard occurs when it is changed from 1 to 0. See, every 1 to 0 there is a static 1 hazard occur. And that's it for our the before part of our part 3, which is this circuit. So after that, I'm going to talk about the fixed version of it, which is that static 1 hazard won't occur. And that's it. Thank you. Yeah, so we know that this circuit will have a static 1 hazard. So that's why we need to change it to a non-static 1 hazard circuit. So based on the K-map, we notice that here they are interlapped. Yeah, these two you can group it together. Hence, we do the calculation here, which is CB, which is these two, the first two, and AB0, which is the second one, plus AC, which is the overlapping, the highlight one. Yeah. So with calculation, we come up with this circuit, which is this is the schematic of the circuit. Yeah, and this is the real circuit here. So it's still the same as the before part. Our A and C is still 1, it won't change, and our B is changed from 1 to 0, 1 to 0. So in this case, you can see from the oscillator that there is no static 1 occur with our new circuit, as when it changed from 1 to 0, there's no static 1 has occurred. 1 to 0, no static 1 has occurred, which means that our new circuit has completely, completely disabled the whole static 1 hazard inside the normal circuit.
Normal hazard.
Yeah, inside the normal static 1 hazard. And that's it.
Thank you.